It is my great honor and pleasure to give this presentation on synergy between X-ray imaging and deep learning. This intersection is highly synergistic. Currently, deep learning is the mainstream of artificial intelligence, which means that we use neural networks for machine learning. So first, let me briefly explain the idea of artificial neural network. On the left, we have a cartoon for biological neuron. So physiological stimuli are collected through dendrite by the cell body. Then the neuron, will decide if the total strength of stimulation is high enough for the neuron to become excited. And if so, electrical signal, also called action potential, will be sent down along the axon through synapse to stimulate other neurons. On the right, we give a mathematical model of biological neuron. We call it artificial neuron. This is a basic processing unit. So input vector contains multiple variables. Xn is the last one. So you have n element. And corresponding to input vector, you have a weighting vector. Also, you have totally n element. And in the first part, this linear processing unit, you perform a linear operation known as inner product. So input vector, weighting factor, you just multiply them together and to produce a single number called the inner product. And this inner product will be processed by nonlinear processing unit shown here. So this is done by a activation function. So it depends on the value of inner product, and the output could be high and could be low, and representing the shell status, and excited or inactive. And there are many kinds of activation functions. Here we show a popular choice called the ReLU function. So shown here, high value you got positive output, otherwise you stay zero. And the basic information processing unit, artificial neuron, it's simple to understand. Then you can link many neurons together into different architectures. And in this case, we have so-called feed-forward neural network. You have an input layer, which is known, such as a vectorized digital image. Then you have output layer, which could be a segmented classified image or some other information, your image analysis results. So between the input and the output layers, and you can have a number of hidden layers shown here. So information processing will go from left to right, step by step, like a water flow. So-called deep neural network is nothing but just the number of hidden layers is very large. Okay, so this deep learning architecture would facilitate multi-resolution analysis and powerful knowledge presentation. So how do you set weighting parameters of a neural network? That's a very important. And this is nothing but an optimization problem. Here is a digit recognition network. Input is a vectorized digit image. Output is so-called one-hot vector. Supposedly, only one element in the one-hot vector will be activated to indicate which input digit is. So since weighting parameters of the network were initially randomized, so output may not be what you expect to see. For example, in this case, you input 5. You know it is 5 because all these weighting parameters are random. So you just do feed-forward computation, and as a result, in the one hot vector, only one element. In this case, this port corresponding to digit 1 give you relatively high output. This is wrong. So you compare with the label. You know the label. So error is 4. So based on the error, you can turn back to refine weighting parameters. And this can be done using gradient descent search and also called backpropagation algorithm. You do it iteratively. So eventually the network will be able to achieve very high digit recognition accuracy. So this whole process is called network training. And after training process is done, the network can be applied to new images. And in my class, and student just spend 2 hours, they can code it their own neural network, and the network performance is very high and can recognize most digit they write on the paper. Take iPhone picture, then network will be able to report what you just wrote. Okay, after that brief introduction, let me present 4 parts in this talk, A, B, C, D. So first one, let me explain general background, basic idea of AI-based tomographic imaging. By a Google search, we see attention to medical imaging. So this is just an orange curve. It's fairly constant. And on the other hand, the hotness of artificial intelligence, particularly deep learning, and since several years ago, is keep going up. And around 2016, you see the intersection. Deep learning, attention to deep learning just exceeded that for medical imaging. So it's around 2016. So in 2016, I wrote a perspective article on deep learning. So we believe deep learning inspired tomographic reconstruction will be a new application and a new frontier of machine learning or deep learning. So machine learning or deep learning first applied in image analysis and computer vision. So you have images as your starting point, then you produce features like classification, segmentation, and tomographic imaging is a kind of inverse process. So you first got a lot of tomographic measurement here, then tomographic algorithm is used to produce images. So computer vision is from images to features, and the tomographic imaging is from features, the tomographic data like line integral, Fourier components, from data to images. Traditionally, and we have 2 kinds of reconstruction algorithms. So you can just write down filtered back projection formula, you derive formula. So image reconstruction can be done based on closed form solution. Later on, and you can incorporate statistical knowledge on measured data and prior knowledge on image content. You do optimization iteratively, and it's time consuming, but you have model-based image reconstruction. So 2 kinds of reconstruction method. So with deep learning, and we see the third type of reconstruction algorithm. So we call it deep reconstruction. So the deep neural network is trained iteratively, like iterative algorithms. Okay, once the network is trained, and you can just process input data and output image in a feed-forward fashion, like analytic reconstruction. Here is a book we wrote on this topic. This is the first book published by IOP. And based on the perspective article I mentioned, we edited the first special issue on deep learning-based tomographic reconstruction. And this special issue was well received and highly cited. We are finishing the second IEEE transactions medical imaging special issue, and we received twice many papers as that we got for the first special issue. Recently, it was reported, and this flagship journal received impact factor and slightly over 10, and partially due to hotness of deep tomographic imaging. And I recently did a scope search, and just use the searching rule, deep learning and medical and image and reconstruct star. You see this very impressive and impressive curve. Last year, we got over 300 publications on this topic. Okay. So second part, so in the first part, I give you some general background, AI-based tomography. Now, let me just give you a few good biomedical imaging examples on denoising, sparse-data CT, and radiomics. Okay. First example is low dose CT, and we know CT is very important, and oftentimes CT scan is the first examination before any major medical intervention is taken. But radiation dose is harmful for human body, and so you use normal dose uh, radiation, you get a decent image quality. But you know radiation, X-ray radiation may potentially induce cancer, cause genetic damage. So we try to minimize radiation dose so patient risk can be reduced. But if you use quarter dose filtered back projection, you see the image become a little noisy. Okay, and the current algorithm, and you use iterative model-based reconstruction. So you take Poisson noise and the image smoothness into account. The image quality becomes a little bit better, but you can still see blurry and some residual artifacts. Okay, so deep learning showed great promise in this domain, and these are three earliest papers, and there are many other papers. So first two papers are the really earliest publication, and the third one, and we use published in TMI, and we use WGAN, and we introduced the perceptual laws and measured by VGG network. So we kind of have human perception incorporated. The resultant image quality looks very much like ground truth. And furthermore, in collaboration with Massachusetts General Hospital, and we designed a modularized adaptive processing deep network with radiologists included in the loop to optimize the denoising strength in a double-blind reader studies. And this deep learning approach and performed either superior or comparable to commercial iterative low-dose CT algorithms on three major vendors CT scanner, including Siemens scanner, GE, and Philips scanner. And our work reported in Nature Machine Intelligence. Okay, over past years, our research has been supported by General Electric, and the initial project was on low-dose CT denoising. Several years ago, GE's deep denoising software was approved by FDA, and here is an example comparing this low-dose CT, and this is the iterative reconstruction. And on the right, and you have true fidelity reconstruction results. So this is a deep learning software. So as the second example, and we want to discuss sparse-data reconstruction in a C-arm CT device or futuristic stationary CT system. And in this case, you have distributed X-ray cells, but the number of projection views is very limited. And in the sparse data case, and the contemporary algorithms using sparsity promotion could do a good job from at least hundreds of projection views. Okay, here is a deep reconstruction network we recently designed, and we call it SUGAR for split unrolled grid-like alternative reconstruction. Okay, so you see just the multi-resolution processing and iterative correction for residual data. And we get very good results in the initial study, just from 36 views. So in comparison with complex sensing, you see typical blocky artifacts, and this sugar reconstruction, you see the anatomical features looks close, very close to ground truth. Low-dose CT is mostly used for lung cancer screening. And in another study we performed in collaboration with MGH, and we analyzed low-dose CT images to assess cardiovascular disease risk. And we got pretty good results. So machine learning performance and compared to all these radiologists reading based on ECG-gated cardiac scan. That's clinical standard. And this deep learning performance, we just do retrospective processing of low-dose CT images. You see the performance somehow comparable. So that is to say, with deep learning, low-dose CT could be used for dual screening of both lung cancer and cardiovascular disease. So although the above three examples are all on X-ray CT, and I want to say the deep tomographic results are also promising for other imaging modalities, including MRI, nuclear tomography, ultrasound, and optical imaging. And if you are interested in more detail, you can take a look at this review paper. And we cited many literatures. With a very strong synchrotron radiation beam, and we see the biological target like a protein molecule could be smashed into a scatter wave. So this is just a biological imaging problem, and what I mentioned earlier, medical imaging problem. So how do you just perform a 3D structural reconstruction, molecular structure from this spherical scattered wavefront? This is very important for drug design and fundamental biological research. And we did some work a number of years ago to perform this reconstruction task with polychromatic radiation instead of monochromatic radiation. And we show the benefit with polychromatic radiation. Very recently, Nature published a very interesting paper called AlphaFold. And this is a deep neural network that takes the protein sequence as input and reconstruct the 3D structure of protein and got very good performance. Certainly not perfect, but this is a giant step forward. Actually, AlphaFold is state-of-the-art prior biological information on the underlying protein structure. So along this direction, and we believe and we could just combine scatter data-based reconstruction and just the sparsity-based reconstruction, and also the prior knowledge derived from AlphaFold, so we can get this intersection, and we can do a state-of-the-art non-crystalline protein reconstruction. So this is a biological sample. The third part, and is see challenges in clinical translation. And in the second part, and I have been very positive about deep learning results. And now I need to say some potential risks and the current challenges, particularly robustness and generalizability. Vulnerability or brittleness or instability of deep networks is currently very hot topic. So here you see two examples. Okay, in the top example, you have this is the mounting image. Then we calculate subtle noises in certain way, and the noise is so weak. We add on top of the mounting image, you got right image and the two human eyes, both left and right image. They look the same as the mounting, but for trained neural network, and this calculation purposely trick the trained neural network, and the neural network will classify left image as snow mountain. That is what we expected. But the right image will be classified as dog with high level confidence. So this is a good example showing deep neural network is unstable. So we want to have a stable performance. And here is a concern for medical imaging, right? This is a very important PNAS paper on instability of deep learning in image reconstruction and the potential risk of AI. In this study, 3 types of instability of deep reconstruction networks were reported for both deep CT and MRI reconstructions. So these instabilities are believed coming from lacking kernel awareness and non-trivial to overcome. However, in this paper, it was also reported complex sensing-based algorithms are very stable due to their inherent kernel awareness. Okay, 3 kinds of instability. So first, 2 types of instability are well-known type 1 and type 2 errors, or false alarm or missing target, as shown as this red and green stars is first 2 kinds of instability. And the third type instability is shown in this cartoon. So it's very interesting, it's unique instability. And this is somehow a fed up problem. That is, more data is used for a trained neural network, but the neural network used to take a smaller amount of data. When you give more data to neural network performance will be compromised. So this is very interesting. How to address all these problems? The general answer is in our perspective article. So we draw this figure 5. So in this figure, we should combine conventional iterative reconstruction algorithm with deep learning component or deep neural network in different ways. So we do not say we do deep neural network. We just use feed forward neural network to do imaging tasks. And we should really take all good algorithmic ingredients from classic algorithms, including compressed sensing algorithms. For example, you do a classic reconstruction, the results are not very good, then you just improve the results by neural network. And you could also combine classic algorithm and the neural network together. And the specific answers are also available. For example, and we have a network, hybrid network. We call it analytic, compressive, iterative, deep network. So just let me explain. So you have tomographic data, okay? Then you use deep recon network, you get initial image. The initial image based on big data prior, pretty good, but this is subject to, say, instability. You have errors and may not be sparse because CIS algorithm, CIS compressed sensing algorithms are very stable due to kernel awareness. So we just filter this initial image, then we sparsify this initial reconstruction. So we get a better result. It filtered image. Then we use analytic operator, which is a system model, and to predict what will be data based on the current image. We compare this predicted data with real measurement, and you see data residue. Residue indicate the necessary necessity for image correction. So this residue data is input to the same deep neural network. So we have an incremental image. Incremental image is added on top of the current filtered image. You get a new image. This new image is filtered again. So step by step, you improve the reconstruction results. Recently, we analyzed the convergence of the ISAD framework I just mentioned. So we assume a bounded error norm property. So we call it a BAM property. Basically, we say this shown here. You have ground truth image, then you have a reconstruction. So the reconstructed image and the ground truth image are not a whole lot different in the L2 norm sense. So this error term compared to the ground truth is less than 1. So we tested all the algorithms in the PNS paper, deep networks there, cited there. So this BAM property easily satisfied. So with this property, we can mathematically prove and this ISAD network converge, and all the details is in the paper. So heuristically, you can just see this figure, okay? You have ground truth image, initial image, you got an error here, and not bigger than ground truth. So this is error artifacts component, and which is observable to a good degree, and because you can measure the residue data. Then through iterative process, so this observable errors is removed. So the error component gets smaller. You do this again and again, and eventually you just improve the image, and to the degree, and you only got a small error components, which is unobservable. And we have this illustration to show the idea. So the deep learning-based reconstruction and define data prior in the red region, and the complex sensing based on sparsity define this green space. Then you do tomographic measurement and use solution all to respect data fidelity. You have this blue space. And with a hybrid framework, as I just explained, and we can find solution in the intersection of these three spaces. Same thing like earlier I mentioned, use use AlphaFold as prior knowledge, and you try to do good protein structural reconstruction. So you find the best solution in this intersection. So this is the idea. So look at some images. So with complex sensing algorithm, CS and acid, we consistently got good results. So we eliminate the first type instability, this is false positive, and as indicated by this red arrow, you have false positive, this blocky thing, and this dots, and also and complex sensing and eyesight could reduce and false negatives. So as indicated by green arrow, this small lettering see totally missed. But in CS algorithm, this small lettering is still here, and eyesight recovers features and even better. So we just did systematic evaluation, and shown here CS pretty good, and eyesight, the green bars, even better in terms of peak signal noise ratio and also structural similarity. So, and the superior performance shown here is due to the integration of all different kinds of algorithmic gradients. So we take complex sensing into account, so we could do a bit better than complex sensing. So the first two kinds of instabilities can be removed. Also, the third type of instability, and we show with eyesight, and because of the special design, if you take, if you have more data available, and with this hybrid design, and the eyesight will give you better performance, and just eliminate the instability, more data. And here with eyesight, we have even better performance measured by mean square error and structural similarity for both CT and MRI. Okay, we also would like to mention another very important and actually related problem, and called generalizability problem. Recently, in a Nature Medicine paper, and some authors discussed how medical AI devices are evaluated by FDA. And a potential problem was reported on the AI models for detecting collapsed lungs. The model was trained on one of these three data sets, red, green, blue. You train the model on one data set, it will perform well on the testing data set collected on the same site. But if you use the trained model, like this case, you train the model in the Stanford data set and test it, you got accuracy over 90%. But you apply the model to the data set collected in Boston area or collected at NIH, the performance drop by about 10%. So this is so-called generalizability issue. And when the model, AI model, is applied to data that have different distributions than what training data base, then you have this generalizability issue. And we are actively working on this generalizability problem. So stability, generalizability, these two things are very important for clinical translation. So for AI to be reliable, to be fair, unbiased, and we need to solve all these problems, and active research are going on. The last part, say a few words on directions for AI research, and particularly I will comment on interpretability so we can hold AI responsible, explainable, and also we talk about the future artificial general intelligence. Okay, this is our recent, quite long review paper on interpretability of artificial neural networks. So all kinds of methods and very important. So we know how AI and usually considered as a black box, and we can explain it to different degree and make it more transparent and turn black box into gray or even white box, so we know what's going on. And I do not have time to explain all these, but you can read this paper. I just want to say some of our work related to interpretability. And currently, all the neural networks use, almost all the neural networks use conventional neurons, inner product subject to nonlinear activation, as I already explained. But in biology, we know we have amazing diversity, all kinds of neurons, even just some simple processings in human perception task involves different kinds of neurons. But why in artificial neural networks we only use this type of neuron? So the input vector, weighting factor, and this inner product, the linear processing unit, then subject to nonlinear activation like ReLU, you got output. This is what we just learned. Okay, and we think we need to make more types of neurons to make neuron types diverse. So this is the initial try. So we got two conventional neurons, multiply together, and on top of it, we add another quadratic term. So we got this mathematical definition. So number of parameters. Here you got n input variable. You have n free parameters for numerical optimization. Here, by this design, we have a number of parameters, 3n. So this is a little complicated, but we got some benefit. So think about a single neuron. And we know conventional neuron, you couldn't use conventional neuron to implement so-called XOR gate. In contrast, our quadratic neuron can implement a hyperbolic function, directly implement the XOR gate. And as a matter of fact, our quadratic neuron as designed can be adapted to implement any two-dimensional logic function. So this is, we have a completeness of this design. So along this direction, we believe that many kinds of artificial neurons can be designed so that we can do specific application better. Okay, and Hinton's capsule idea, I think, is also in a similar spirit. You make a processing unit adapted, specialized, then you could have better performance. So in perspective of De Morgan's law, so the negation of a disjunction is a conjunction of negations, and inspired by this duality, and we systematically analyzed the family of ReLU networks and proved that the network widths and depths are quasi-equivalent for either classification or regression tasks. If you are interested, you can take a look at our theoretical paper here, and you can find several theorems and their proofs. So that is to say, if you have a given complexity of neural network, you can make a very wide one, very deep one, or many between. All of these networks will essentially do the same job. Like you have a set of Lego blocks, you can build a skyscraper, you can build a flight playground, you can build many kinds of houses between. Since our quadratic neurons are continuous instead of being binary, we tend to consider them as a fuzzy logic gate. Whereas a deep neural network is nothing but a deep fuzzy logic system. A digit recognition network is shown in this diagram. Okay, the size of each neuron shows the relative importance of the neuron. Okay, then the color of a quadratic neuron shows the type of its fuzzy logical operation. For example, is the neuron hyperbolic or parabolic, as determined via spectral analysis. So with the deep neural network interpretation, so this neural network is kind of a fuzzy rule-based system, right? So to be really a human-friendly rule-based system, we should further compress or transform a deep fuzzy logic system into a knowledge graph. So this idea could be a way to link connectionism and symbolism, data-driven and rule-based system together. If so, this approach could offer a greater interpretability of deep tomographic reconstruction. We believe that knowledge graph is a very important field, and if we develop a good method to combine to transform deep fuzzy logic system into knowledge graph or dynamic knowledge graph, that will be a step forward towards so-called artificial general intelligence or strong AI. Towards strong AI, an AI system would behave more like human. Last month, a deep Omni-Perception system was published, which processes images, text, and audio files all together. So this is achieved with token-based embeddings, multi-task pretext learning, and multi-granularity integration. A very nice work. And this reminds us our earlier work on Omni-Tomography proposal, in which we hope to achieve a grand fusion of relevant tomographic imaging modalities. By such fusion, multi-modalities are integrated into a single gun track and collect diverse data set at the same time. As a result, spatial temporal correlations are ideally captured. However, this idea appeared to be very expensive and data limited, given the bulkiness of individual imager and the tight space for hardware integration. Thanks to the rapid development of medical imaging and deep learning technologies, the situation is now quite different. The company NanoX reports cost-effective X-ray imagers for tomosynthesis. Hyperfine is the brand name of low-field portable MRI scanners. Also, photon counting detectors record both X-ray and gamma-ray signals to unify CT and SPECT imaging. Hence, it is feasible now to integrate these cost-effective imagers together into a cost-effective omni-tomographic system in deep learning framework aided by GPU. This could be a next highlight of medical imaging, featured by portability, point of care, and power unleashed with auto-driving cars to deliver imaging service wherever needed. This is particularly important for underdeveloped countries and remote areas. As I close this presentation, I would like to leave you with a thought about the future. In the scientific fiction, Siren of Titan, the author wrote, and I quote, "Once upon a time, there were creatures who weren't anything like a machine, and these poor creatures were obsessed by the idea that everything had to have a purpose. These creatures spent most of their time trying to find out what their purpose was. And every time they found out what seemed to be a purpose of themselves, the creatures would make a machine to serve it." Okay, let's all do our best to develop a better AI and improve our imaging service and health care for humankind. Thank you so much for your attention, and I'm deeply grateful for my brilliant students and postdoctoral fellows and long-term collaborators. I'm open to interact with you and seek potential collaborative opportunities. Thank you.